Coming through on the microphone? Can you tell if I'm coming through?
Yeah.
Okay. So as you can see, we're having some slight technical difficulties. There's somebody on their way over here. But I'm going to start anyway, just because I don't want to have to wait too long. A lot of what I'm going to say for the first few minutes, you know, I always talk with PowerPoint slides in front of me. That's just kind of, you know, what I do. But most of this stuff is information that's on the wiki anyway. There's no reason why you have to get it in 2 channels. We can just get it audio. If you really like looking at PowerPoint slides, or you just like sort of feel a little bit twitchy and uncomfortable if you're at a class and there's not PowerPoint in front of you, if you go to the course wiki, all right, and the easiest way of getting there is to just Google Cohen CMU and then look at my teaching slot, and there's like a link directly there to the wiki, okay? So once you get there, there's a syllabus page, and on the syllabus page, there's a link to a page for each lecture, and on that page, there will be a pretty much up-to-date PDF and PowerPoint of this talk. So if you want to look at it and you happen to have a internet-enabled device handy, then you can certainly do that. For now, I'm just going to talk, okay? All right, and you can just like get the visual stuffs later, okay? So, so the first thing I was going to do is basically say so who we are, who the instructional team is. There's a bunch of people involved. I'm William Cohen. My assistant is Dorothy Holland-Minkley. She started at CMU last week, or she started in our department last week, but she seems really smart. So she'll help out with like distributing assignments and, you know, getting hold of me and things like that. Okay. We've got a great team of 8 TAs, okay, that I'll introduce in a couple of minutes. All right. So one thing that people might be curious about, or the biggest question I've gotten is, will I get into the class? Okay. And the answer is, I don't really know. Every other year I've been here, the wait list is eventually cleared. Okay. This is more people than I've ever had before. Okay. So there are actually 330 people that have expressed an interest in this course, either by signing up or being waitlisted. This room, as you can see, does not hold 330 people. We're not really allowed to like sign up more people than the room holds, although we're going to bend that a little bit. So I'm hoping the wait list clears, but I can't promise. If you really want to take the course, all right, then what I will encourage you to do is to attend the lectures for the first few weeks. Okay, so I just had a discussion with Garth Gibson, who runs the master's program here at SCS. If you're a master's student and you're on the wait list, you will be able to add after the regular add deadline. So Garth thought like up to 4 weeks would probably be okay. After the regular add deadline, basically it's a big hassle. So he has to individually sign something. There's a piece of paper that gets filled out and so on and so forth. But it's not impossible yet, okay? If you're a PhD student and you want to attend and you're waitlisted or something, then send me an email. Probably you should be signed up for 805, and there are slots for 805. If you're an undergraduate and you want to attend and you can't get in this year, again, send me an email. If it's your senior year, we'll kind of like talk about it and work it out. So this is something we're aware of. I'm sorry it's so big. I can't teach it next spring because I'm on leave next spring. So the next time it will be taught will be fall when I get back. Okay. Questions so far? Okay, cool. Next I was going to do is basically say a few words about myself. So I got my PhD in 1990, and I worked at Bell Labs for like the first 10 years of my career. So that was actually an interesting place to work because at the time AT&T had what were, you know, huge data sets for machine learning. This was just when sort of machine learning and data mining was getting to be a thing. So I remember one of the big projects they had, which was pushing the envelope of all sorts of technologies at the time, was they built basically a few very simple classifiers. And they tried to classify every phone number that they knew about, not just their customers, but every phone number that was ever like passed through their system. So they had classifiers to tell whether it was a fax machine or whether it was a business versus a personal account. That was hundreds and hundreds of millions of entities. And at the time, it was like sort of a big deal. But there were lots of problems that were really big. And I was kind of intrigued by these because it seemed like a lot of the things that people knew about in academia and thought, well, we've kind of got this problem solved, we know how to do it, just basically didn't work when you went from a few thousand examples to even a few tens of thousands or hundreds of thousands of examples. So after AT&T, I moved to Pittsburgh. I worked for this startup called Whizbang Labs, which did information extraction from the web. I'm still doing information extraction from the web, so I guess that was a good thing. I didn't get rich, so I guess it was a bad thing, but so it goes. I've been at CMU since 2002. Next semester, and also 1 year in like 2008, 2009, that range, I spent time at Google. So I was a visiting scientist at Google for a year. And that's basically when I started this course. I came back from a year at Google, and I realized that there were a lot of things that people sort of needed to know in industry that we weren't really teaching people. So our AV person is here now, so that's great, right?
Oh, don't clap yet.
Oh, but wait, he says don't clap yet.
Okay.
All right. So the next thing I want to do is introduce the TAs for this course. Okay. So I had like them all send in one little slide, which you can look at online. But maybe we'll just rather than staring at their pictures up there, maybe we can actually stare at the actual physical human being, right? So Bhuwan, do you want to raise your hand, stand up or something? This is Bhuwan Dingra. He's a PhD student. This is his second year. He took this class last year when I taught it. He's working with me and Ruslan Salkutinov, who's like a deep learning guy that just came to CMU. He focuses in his research on deep learning for NLP. He says he enjoys hiking and traveling. The other thing on his little slide there is it says he's a very calm person. So don't hesitate to ask him questions. So there will not be any sort of violent physical retaliation if you ask him questions. I have to say none of the other TAs mentioned that, so Bhuwan's a safe choice. All right, I'm going to take a couple of seconds here to mess around with this and see if I can get.
Give me half a moment. I'll get it up and running.
Yeah, okay. I think we can get here, right? So we just need to
get
the mirroring set up, right? Now we're I just couldn't figure out how to turn it on. That's all, right?
It was, long story short, they used to turn on with a touch.
Yeah.
There's a button now on the side that turns on. We have to react.
There's a button on the side.
So people turn it off accidentally.
Yeah. So it was a hardware problem, guys. It was a hardware problem. It is not my fault.
This connection wasn't seated right. That's why.
And the connection wasn't seated right. It was two hardware problems.
There you go.
Okay.
Have a good day, sir.
All right. Thank you very much for rescuing my butt. Okay. All right. So that's Bhuwan. Karandeep, are you here? There's okay, Karandeep Johar in the back there. Okay, so he's a master's student in the CS department. Okay, he also took the course last fall or last spring, I guess. So I got to say, all the TAs took this course and did great. So they really understand this material well. Len Zhaozhu, sometimes known as Karen. So she's a master's student in the machine learning department. So she's doing her data analysis project with me and a buddy of mine, Bob Kraut. And she says you'll learn lots of awesome things here, okay, which are constantly used in industry. Su Ming. This is Su Ming, okay? So he's another second-year master's student in LTI. He's got some practical experience. He spent some time at LinkedIn. Chen Ran, over there in the back, monitoring the exits, acting as our bouncer. So you can't come in unless you have ID. He interned at Google, and apparently the only thing they're letting him say is that he played Pokemon Go. I don't know, it must have been a really exciting project. That's a great place probably to like catch like Pokemon because, you know, everything's wireless there. You're not biting into your data plan, right? So Jingyuan Liu is maybe there's like one or two people that are not here yet. Okay. So I believe he's going to be here next week. He is in the MIS program in LTI, which is one of the smaller programs. The students there spend a bit of time doing research. He's working with Eric Singh, who is another data guy here at CMU. He's working on this thing called a predictor server. We'll talk a little bit more about later this semester. Yuzing Zhang is the gentleman working the camera over there. He's another master's student in MLD, also doing a DAP with me on kind of deep learning stuff for modeling knowledge bases. He's not, as you see, he's not actually quite as tall or thin as he looks in this slide. You look good. You look good. Strong. Yulan Wang. Is Yulan here? Yulan is there in the back. Okay. So Yulan Wang is in the master's program in LTI as well. It's her second year as well. Okay. So that's our team. Okay. So let me talk a little bit more about what kinds of things we're going to do and how we're going to do them. So this is a very languagey sort of class. I have a joint appointment in language technology. One thing I like about language tasks is the data usually makes sense. One of the interesting aspects of working with big data is the data you're working with gets to be a little bit harder to see and visualize. We'll talk a little bit about more of this later, but you know, for some types of data like large graph data sets, you can't even sort of easily subsample it and look at it, right? And one nice thing about language tasks is we all in this room can speak English, right? So the data usually make a little bit of sense to us. The models usually make some sense. It's also often the case that when you look at linguistic tasks using these statistical models, the models that work best are really complicated models, right? Which means that you really are in a situation where you need a lot of data to do well. Okay, so these really are kind of naturally big data problems. Okay, and of course, it's also interesting because when you have a very simple model that just has maybe 10 or 100 parameters, the computational properties of learning that model can be quite different when you've got a really large model. When I started this course, pretty much everything was in Java. It was in Java because we're working with Hadoop. So we're going to be doing more stuff in Python this year as sort of the maturity of the kind of big data stack progresses. I'm sort of forcing people to go down into the stack to like sort of the Java Hadoop level less and letting them do more stuff sort of higher up. We'll be working with a couple of clusters. We will be doing a lot of assignments on the Amazon Elastic Cloud. I'm curious to see how many people have worked with the Amazon clusters before. Okay, pretty large number. Okay, how many people have done that? Like, how many people have taken the cloud computing course here? Okay, similar set of people, right? There's also something called Open Cloud, which Garth Gibson runs. So this is a local cluster. It's not ideal for assignments for a course like this because, when you get like, 200 people working on something the night before it's due, it's just not quite big enough to kind of handle that. But it's much more convenient when you're working with Elastic Cloud. There's basically some setup you have to do, which takes a few minutes before you can start working. So it's kind of like your machine. I mean, it's on the web, right? But it's kind of like your machine is like sort of like a block or two away. You've got to walk there to get to it. So Open Cloud you can get to immediately and log in, so it's a little bit more convenient to work with. And there are also going to be some of the early assignments. Actually, several of the assignments are basically just things that you can do. Will be big data ideas, but you won't have to use them to run them on a laptop. So you will need some disk space. Okay. So if you don't have space on whatever machine you plan on using, you might want to go in and delete one of those movies or something. I don't know. Okay. So questions? I'm going to ask some questions to you guys. So how many people in this room are undergraduates? Raise your hand. Okay. Seniors? How many are seniors? How many are juniors? Okay. How many people are master students? Yeah, okay. That's typical. Okay. So how many people are in the computer science, CSD program? How many people are in one of the LTI programs? Okay. How many people are in the machine learning department's MLD program? Okay, welcome. Yeah, how many PhD students do we have here? Okay, okay, very good. All right. So let me talk a little bit about there's actually 2 courses going on here. So 605 is a lecture course. Okay, the bulk of this, the grading is homeworks, midterm and final. Okay. The homeworks don't really require doing a lot of implementation. It's not like thousands of lines of code that you're going to be writing in big groups or something. It's not a software engineering project. But be warned, when you're working on machine learning programs in general, it takes an inordinate amount of time to get them right. So it'll take you some time to get them right. So make sure you kind of allocate time to do the programming. And this is something, there's always going to be in a class this big. There's a huge spectrum in how fast people are at programming. It's like if you line people up and have them run a marathon, some people will be done in like 2.5 hours. Some people will still be kind of chugging across the finish line at 6 or 8. So, if it's going to take you time, make sure you allocate the time for that. So there's also 10805. Okay. So that's designed for PhD students, although it's open to master students. If you'd rather do 805 than 605, you can do it if you're a master student. You need to send me your CV, and I need to give you permission. And there's only a certain number of slots for 805 because 805 students do presentations and projects, so it's an extra load. But if you want to do it, send me a CV and ask for permission. Okay, so 805 students, basically, it's kind of the same for the first half, and then they do the project, so they don't take the final. There's a project which is 40% of the grade. All right. So in past years, we've done, I would say, with sort of big success, sort of an intermediate thing. So if you're an 805 student and you're doing a project, and you think it might be fun to do a slightly bigger project with some people that know how to program to kind of help you out, then talk to me. If you do, then then we can advertise that, and we'll get we'll give you, the rest of you guys, the 605 students, a chance to collaborate. All right. So what you get, in addition to the fun of working on a research project, okay, is you basically get paid one assignment and the final. Okay. So you don't take you don't do the final. You do one less project. Okay. And the expectation is you won't be, probably defining the problem, right? But you'll be helping sort of exploring solutions with it. And we'll talk about the matchmaking, but the 805 students have roughly a month to figure out what they want to do, and we'll start doing some sort of matchmaking based on that. Okay. So quizzes. Okay. We are going to record the lectures. We're recording this lecture. Okay. And the lectures are going to be up on the web. We'll tell you how. Okay. So you should keep up with lectures. And if we record all the lectures and there's this unfortunate tendency, it's like, well, I'll just watch the video of that lecture, when I finish with this assignment, or when I'm done with this Pokemon Go goal of mine. We don't want people to kind of fall into that hole. So the 5% class participation is so that you know it's important. It's to kind of keep you honest. So what there'll be periodically quizzes. My personal life goal is to have a quiz for every lecture. Okay, so after the lecture, you'll go and do the quiz. They'll all close pretty soon. The one I put up now closes, I think, tonight at midnight. Okay, so we'll just sort of see how that goes. And these are not, the total of the quizzes is 5% of your grade. And let me tell you even further, it's like whether you get them right or wrong does matter. But what I really care about is whether you've done them or not. Okay, so do the lectures, think about them enough, and do the quizzes. So it's a check that the lectures go into your ears and at least part of it bounces off your brain. Okay. So projects, I guess we've sort of evolved over time. You don't really need to know too much about this. But basically now, if you're doing a project, you need to be an 805. If you want to do a project, you should be an 805. So if you're not signed up for that and you want to be, let me know. Okay. Okay. So this is my least favorite part of the first lecture. Hopefully, this is the only time that I think about this during the semester. Because when I do have to think about it, it just always bums me out. I have this long explicit policy on the web page. Go look at it if you want. But basically, the short story is you're invited, you're encouraged to talk about things among yourselves. Okay, it's okay to sit down and do the quizzes together if you want to kind of talk about things and do the quizzes in groups. All right, that's fine. Okay, but everything else, I want you to do on your own. All right. So Roni Rosenfeld's clever idea is basically you're not allowed to transmit any information except by basically downloading it from your friend's brain into your own brain. Okay. You can't take a shortcut. You can't put it on a piece of paper and then just take the piece of paper. You can't put it on a thumb drive. It has to be mind to mind. Okay? The other thing that we ask is that if you're either the recipient or the distributor of information this way, or ideally both. Ideally, you'll be sort of collaborating and talking about things. Then you tell us. So when you turn the assignment in, say, I had a discussion with so-and-so, we discussed this thing, but I did the work myself. Okay, so whenever there's any discussion about technical material, you say who you discussed it with. Okay, the cases that will be exceptions will be things like projects, and not very many of them. Okay, so here's my policy. So some faculty, and if you get caught in an infraction, then you get a 0 on that assignment. All right. So my theory is that's not because you're going to get a 0 on the assignment anyway. So then cheating is just sort of like one more option. It took me a while to realize this, but it really does hurt everybody when some people cheat. Okay. So you all are here at CMU. You maybe did a lot of work to get here. You're maybe spending a lot of money to be here, okay? And at the end of it, you want to go out and be able to say, I'm at CMU. I got my master's at CMU. I got my PhD at CMU. My undergrad at CMU. It's a good place, and people will say, wow, that's great, okay? You want people to have that. You want to have that reputation when you get out, okay? And everyone that cheats is sort of stealing a little bit of that reputation, okay? So I don't tolerate it at all, okay? And I'm active about looking for it. There is software now that will do a pretty good job at looking at, assignments that have been handed in and figure out whether there's overlap. Even for a class this size, you can do that. So I don't tolerate it at all. Unless there's some really weird extenuating circumstance, which there usually isn't, you failed, okay? All right, regardless of whether you fail the course or not, then it gets reported to the Office of Academic Integrity, which goes up to the head of your program, the dean of the school, and I think even further up than that. They basically kind of keep the first file that nobody else sees. So you usually get one strike, okay? And the second strike, you're usually expelled. Again, unless there's some weird extenuating circumstances like the original thing, and signed up, right? Had 2 infractions in different pairs, right? And they all got expelled. Okay. So don't be that person. Okay. Okay, another administrative thing that's kind of boring to talk about. So some people may tell you it's possible to take this course without taking 601. All right. This year, there's a new director of the master's program, Garth Gibson. He's a database guy. He's the guy who invented RAID, basically, 15 years ago or something. He likes doing database stuff, right? It used to be kind of hard to tell if people were, signed up for their co-requisites using the CMU database system. Garth is like all over that. So we can check this now, all right? So you really should have already taken 601, 701, 715, 401 if you're an undergraduate, one of the intro ML courses. If you haven't taken one of those courses, you should take it now. The course is designed so you should be okay. Maybe you'll have to do a little bit of extra reading here and there, but you should be okay taking the courses concurrently, okay? But the lectures are very carefully designed to complement material in 601. So if you just take this course and you don't take 601, you're learning how to do something, but you're not really learning why, right? So it's not really sort of a productive thing. It's not intended to replace 601 in any way. It's meant as a complement. So if it's a prerequisite, you need permission, right? You send me an email to this address, hopefully, so I can track it. Okay, we will check. Okay. So that's it for administrative stuff. So do people have questions about the administrative stuff? Yeah.
Are the exams in class, the final?
Yes. Good question. What I've done in the past is there is an in-class final exam the last day. Okay, and there's an in-class midterm exam. Other question?
If you want to do the project, then should we get back to the TAs, if I want to skip the final exam and do the project?
Right. Okay. So there are 2 ways of doing that. Okay. You can either say, well, I'm going to do a project. I'm definitely going to do a project. I know what project I want to do. Okay. And choose a project that you're going to do. Send me email with your CV, and I can sort of some master students are more prepared to do, define a research project than others, so I want to sort of verify that. It's also, I should say, projects, I encourage them to be in groups, okay? So you should do a project in a group of 2 or 3 people, okay? 4 is sort of a little bit too many, but 2 or 3 works well. And if you aren't sure whether you want to do a project, or maybe you'll do a project if it's interesting or maybe not, then you can also hang out and see if there's sort of a slot for a project in 805. Or from an 805 student.
Do we get to tell you about it? Because what if we decide after 1 month what we are going to work on in a project? Is that?
You can tell me basically at any point. So I'd prefer that you tell me within the first month. I mean, particularly if it's going to be a switch from 605 to 805. There's paperwork, okay? So I hope most people decide early on whether they want to initiate a project or not, or be part of an initiated project. You don't have to decide what the project will be for another month, but you should decide if that's what you want to do, okay? Okay, other questions? Okay, so now I finally get to talk a little bit about technical stuff, all right? And since I'm an old guy, I'm going to start with some old technical stuff. In 1993, if you can believe it, I wrote a paper on big data. It was actually kind of a negative result. So I looked at some rule learning algorithms that were out there in the literature, and I didn't say this in the paper, but really what I'd done is I tried them on some, AT&T data sets, which were which companies were going to switch to, Sprint, over the next month. So they were big data sets, and these algorithms basically just didn't finish, right? So I tried to figure out why that was true, and you discover this really interesting thing. If you look at linear learning time for this algorithm I was looking at, commonly used algorithm, then it was pretty much linear if you gave it nice, clean data. If you gave data that was pretty noisy, so here it's the same data set, but I just added like, I guess the bottom line is 2% noise, the top one is like 10% noise, then suddenly the learning time just sort of shoot up, right? It's no longer linear. It's something much worse, all right? So what these algorithms were things like this. So the way you would read this is the hypothesis is sort of like a decision tree. So they go through these rules in order. It says the document should be labeled talk announcement if the words contain the symbol talk, or if the words contain the symbol subject talk. And that was like sort of a special thing, which basically means the word talk is in the subject. Or, if it's a talk announcement, if these conditions hold. So 2D416 is where we had all our talks back at AT&T. So this was basically just my data, from a public message board at AT&T. All right. So these are the different rules that you had. And then the default, if none of these rules fire, that were non-talk announcements. All right. And those numbers are basically sort of how often the rule fired and how many times it was right and wrong. So this fired 391 times. So 391 times you didn't get to any of these lists, and it was almost always right. I think you made one mistake. Okay. So the interesting thing is the CPU time, right? So it's the process gets very expensive when you get things that have any noise in them. All right. So let's look at what the algorithm actually does. All right. So this was back in the old days of machine learning. We did a lot of discrete search. So what you'd do is you'd actually start with this rule set. Basically, when it says everything's a talk announcement, and then if that rule doesn't fire, then it's not a talk announcement. All right, so this rule always fires, so it classifies everything as a talk announcement. And then you gradually sort of change this rule set. And what you do is you basically add conditions one by one in a greedy sort of way. So you look at the best condition to add according to some information gain type. Very much like decision tree learning. You've done 6 of 1 and heard about this. So you look at all the word conditions you can add, and you add the one that sort of seems to help the most, and then you greedily add another one, and so on. At some point, that rule is going to be accurate enough that it doesn't cover negative examples. So whenever you add a condition, you're reducing the number of things that it fires on, okay? So that you're making the rule much more and more specialized, okay? And when you get to something that basically doesn't cover any of the negative examples, you stop and you kind of construct a new rule, all right? So you do something like this, and then afterwards, and this is something that was done because experiments suggested the right way to do the search was first build a complex rule set and then simplify it. So you could imagine, well, I'm just going to sort of like figure out where I want to stop, but it turns out to be a hard thing to do. It turns out to be easier to do 2 phases where you start with this big, messy rule set that you've learned, and then simplify it. Okay, and the way you simplify it is you basically go through and look at things that you added that you can take off without changing the coverage too much. Okay, so you go back and delete a few conditions here and there. Maybe you'll delete an entire rule. Okay, and then you end up with a more simplified, concise rule set, which isn't quite as accurate on the training data, but hopefully will generalize better. All right. So that's the algorithm, and let's take a little bit of a look at how this is going to work. All right, so let's imagine that I'm going to iterate over this growing phase. All right, so the number of times I iterate will be m, so that's the total number of conditions in the rule set. So this rule set here has, I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9 conditions. Is that right? Did I count that right? So here the iteration would be 9. All right. So when you pick the best, it turns out the naive way of doing it, and for various reasons, sort of the most efficient way of doing it, is you look at all the examples and you evaluate that condition, right? So the time to build the rule set initially is at least m, M is the number of conditions you add, N is the size of the data, okay? So the problem is when you have noise, okay? So if you have just pure random noise, if I just give you like a bunch of examples that are just labeled, uniformly at random with talk and non-talk, then statistically, that's incompressible. If I give you just random noise and you try and run it through gzip, it's not going to get any smaller. Okay? The way compression works is you look for regularities and use that to compress data. So this is a kind of compression. You're compressing the labels. You're coming up with a concise rule that explains these things. And if the data is noisy, you can't compress that noise. So that even if there's like 10% noise or 1% noise, there's some part of the data you're not going to be able to compress. Okay? And you can see that because what happens is the system is going to build rules that just cover 1 or 2 examples. All right? So if you've got a huge noisy rule set, you're going to data set, you're going to build a huge rule set. Okay? So this time, the time it's going to take is not linear but quadratic, because M is going to be about the same as N, the number of examples. Okay? And it turns out the pruning phase is even worse. It turns out to be cubic. All right? And you can sort of see this. A nice way of seeing this is to look at the runtime of the algorithm on different size data sets and plot the runtime in log-log space. All right? So then in log-log space, any polynomial looks like a straight line. All right? So this is runtime for this old rule learning algorithm. The implementation is not mine. It's something called C4.5 rules. All right? And you can see it's more or less a straight line in log-log space. Okay? And it's pretty much parallel to this line right here, okay, which is a cubic line. So that's an n cubed line. Okay? Right? And then this was this new algorithm that I eventually kind of came up with. Actually, these are both new algorithms here. Okay, and you can see these are sort of parallel to this other algorithm, which is something like, linear with a couple of log factors. Okay, and the asymptotic complexity makes a huge difference here. So this is like giving you the time it takes to run. Okay, and basically, in log scale you kind of forget, but we're looking at really, really long run times when you get to large examples. Large sets of examples. Okay, so this is just a way of kind of telling you kind of where we started from. So back in the 1990s, there was a lot of work on machine learning. Most of the data sets we had weren't really even big enough to sort of look at complexity. Okay, most of them were pretty small. Okay, and a lot of the algorithms that people used were asymptotically pretty slow. So cubic is really slow if you're looking at large data sets. Okay, but because most of the data sets were small, nobody really cared. Okay, it wasn't really something a lot of people were looking at or even noticed. All right, so people started looking at that in the 1990s. I want to skip ahead to another result. This isn't mine. It's by these guys named Banco and Brill. Eric Brill was the author. He was at Microsoft Research for a long time, and he did these experiments and gave a great, interesting pitch about the results. Okay, so what they did, the task they were looking at is one where you could easily generate lots and lots of training data. Okay, so what he was looking at is what he called context-sensitive spelling correction. All right, which basically means looking for cases where a word is misused. All right, so the words affect versus effect are one example of a pair of easily confused words. People sometimes make a mistake, and working at Microsoft, it would be kind of nice to say, well, let's write a little tool that'll put a little squiggly green line under the word when you use it wrong. Okay, so you can turn this into a learning problem. Okay, the learning problem is basically whenever you see one of these words, affect or effect, you classify it. The features you use are the context, the words around it, all right? And the class you want to give is the word that the user really meant. Okay, so whenever you see affect or effect in context, you'll basically predict which one is appropriate, all right? And you can generate a lot of data because you can just take any well-edited text that doesn't have too many affect, effect errors, all right? And every time you see the word affect or effect, that's a training example, right? So if you've got big corpora, you can get big data sets, all right? So he did these experiments, okay? So a number of people had looked at this problem. In the past, a couple of different methods have been proposed. So perceptron, winnow. Winnow's a lot actually like logistic regression. Naive Bayes, we'll be talking a lot about that. Memory based, so these were like KNN type neighbor algorithms. All right. And you know, somebody had written a paper that said, well, the KNN algorithms work best, right? And they did an experiment which basically said, well, no, actually, if you scale up the amount of data you have, then actually KNN algorithms work worst, okay? Everything else is sort of about the same. But more to the point, okay, what really matters is not which algorithm you're using. What really matters is how much data you have, right? So even using the worst algorithm here, okay, with 1 billion words of training data, okay, is better than using the best algorithm here, okay, with only, say, 1 million examples, okay? So what really matters in terms of and Eric Brill's way of pitching this was to basically say, well, you know, you guys in the ACL community, you're spending too much time looking at fancy learning algorithms for parsing and stuff like that. You should just be labeling more, okay? If you're a graduate student, don't waste your time working on learning algorithms. Like label all our graduate students had them labeled data. We'd all be better off, okay? So all the graduate students disagreed. But it's an interesting point, okay? And the point is that basically there's no data like more data, I guess. The other interesting experiment he did was basically looking at the size of the model that was learned, okay? Which would be here basically the number of weights you have for context words, all right? Okay, as you get more and more data, okay? So why are these things improving? They're improving because they're learning more stuff, okay? They're learning more kinds of models, all right? So the models are getting larger and more complex, and you can see that's still even happening, you know, sort of between 500 million and 1 billion words. It's still learning more trading, okay? So the other thing is, it really is a lot to learn, okay? So there's a reason for looking at all that data. In the interest of time, I think I'm actually going to skip this little comment. This was basically, he basically said, well, you know, even if you're doing active learning, so you're basically soliciting, you know, you're cleverly choosing the examples you're going to get labels, it actually still makes sense. You're better off doing active learning. A small number of labels, billion word corpus, using a small number. All right, so this was basically saying active learning is not going to solve that problem. Okay, so this is kind of an story, Eric Brill's story. I'm going to spend a little bit of time making this story a little bit more concrete. I'm going to just kind of jump out here, if I can. I'm going to try and pop up a window here. All right. Okay. All right. So 2001, this was like a paper. It was like a bunch of work. It's less work now. So they're big corpora that we can sort of easily get and grab. There are lots of good tools for kind of distilling them. I took a big corpus and looked at all the 5 grams of words that had affect or effect in the middle, okay? And I wrote this little tool that lets you sort of explore what that data looks like, okay? So one thing you can do is you could just basically say, well, how often do I have the word affect or effect? Which one is common, okay? So this is basically telling you what the frequency is. So I basically didn't consider case here. So it looks like effect happens like 19 times out of 20 roughly, and affect happens like 1 time out of 20. So one word is much more common than the other. All right, so you know, first order of approximation, do you mean affect or effect? Effect, right? And the rest of these things are all like sort of cases. Okay, so this is telling me how many n-grams matched, right? So this is the total number of things in the corpus, and it looks like it's maybe 91 million, something like that. Okay. So the next question I want to ask is, well, let's look at the rare word. Let's look at effect. So if I have effect in the middle, what comes before it? Whoops, I'm sorry. let me get this right. Well, let's say the rare word is affect. So let's see what comes before affect. All right, so the most common thing is not, and then after that to, and then may, they, in which way. Okay, so these are all like now getting to like kind of 1%, right? But here's another sort of like observation. It's like mostly you see not, in front of affect, you'll see not affect or to affect, right? What other things kind of are going on around there, right? So let's kind of look at what the data says, right? So if I want to find out, well, what happens, in front of not effect? So, all right, well, that just doesn't happen, right? Interesting. So that never happens. So not is like a really good word. How about to? That's the most common thing. Oh, hang on, I think actually, hang on a second. Here we go. There's got to be, not, here, this will be better. Yeah, okay, so again, let's look at this after them. All right, so whenever you see not, you see affect like 96% of the time, and hardly ever effect. All right, I think I miscounted my little dashes here. Okay, so this is a way of kind of exploring this space. So seeing what's kind of in this data set. So I guess what we've learned from this at this point, what we've learned is, from playing with this data, here's some of the regularities, okay? The most common word here, the most common class is effect. All right, the most common word before affect is not. All right, we can also like sort of see like after not effect, the most common word is a, so it would be like not affect to change, something like that. So this is kind of why more data helps. So if I'm looking at a task like this, okay, I want to find out, how these various contexts interact with each other, how they affect the class label, and there are lots of subtle effects, right? Or maybe subtle affects. I'm not sure, but there are lots of ways that these things change, and it's very easy to get into conditions where only one, even with just like one or two, by pinning down one or two words, that only a small amount of data is represented. Let's again kind of go back to that screen here. Okay, so we started off with 91 million n-grams. Okay, when I get down to like, well, what comes after not effect? All right, so we've got a or it or his or this, right? But more interestingly, it's like we're down already to like 100,000 n-grams. Okay, all right, so just by choosing these two words, right, one of which is sort of the most common, class, right? We've gone from 90 million to sort of a few tens of thousands. Oops. Okay. So so this data that I use is actually one of the data sets we'll be playing with in this class. It's called the Google Ngrams data. How many people have heard of this? Yeah, so it's kind of cool to play with. They have like a web server set up where you can download all the data. You can also run little queries. So their data is time-stamped by year, and it's all the n-grams from some large collection of books, right? So you can see how often people say Merry Christmas versus Happy Holidays, okay? So from this, it appears like the war on Christmas has not been going well, okay? My people are clearly losing. Here's another thing. Over time, you're looking at the frequency of the phrase. I don't know if you can read that. It says explosion in popularity. Okay. This is the frequency of the phrase upward trend. That's supposed to be ironic. Okay. This is an XKCD comic which analyzed. It did a scatter plot of the frequency of the word sustainable over time. So this is when the comic came out, which was like a couple of years ago. Then they extrapolated, how frequently it will occur over time based on this linear fit. So in 2061, within our lifetimes, it'll occur about once per sentence, okay? And then, another 50 years, all sentences will just be the word sustainable over and over again. That's a linear regression for you. Okay, so let's go back a second to this this story here. So this basically says there's no real data. There's no data like more data, okay? And for many tasks, there's not really a substitute for using lots of data. There's not really any way of building, a model that will capture all the subtleties of English and how even like just these two words are used without sort of seeing a lot of examples of how things are used, okay? So that's from 2001, and let's sort of fast forward another few years, okay? So in 2009, there's a pointer to this on the wiki page. So I'm not going to test you on this, but I strongly suggest you read it. It's a great story. So this is by Peter Norvig, Fernando Pereira, Alon Halevi. Fernando and Alon and I work together at AT&T, and they're all at Google now. And their paper is called The Unreasonable Effectiveness of Data, okay? And they basically talk about why it's important to use an NLP-centric or a machine learning-centric approach to NLP. And more generally, lots of other tasks, okay? So, they talk about, sort of math envy or physics envy. So, you look at what Einstein wrote down, there's this beautiful, simple formula, right? It sort of extrapolates everything you got, A equals mc squared, okay? So somehow it feels like that's what the ideal scientific discovery is, some really simple mathematical core behavior that you can model very simply, okay? But it seems like a lot of the phenomenon that we're studying now, that just doesn't seem to be the right model. If you look at models of how biological organisms work or how neural processes work or how human language works, the answers are not E equals mc squared simple equations, okay? The answer is there's an ocean of detail, okay? There's an ocean of detail, and somehow we've got to get our hands around that detail. You're not going to do that by sort of writing a whole bunch of equations. The only way to do it is exploit data. So the only way to get to that complexity is by processing data. And the real simplicity, the elegance of our models, if there is an elegance to our models, the elegance of our models is the models that we use for processing that data and learning from that data. Okay. So they say we need to embrace complexity and make use of the effectiveness of data. So just skipping forward a little bit. I was really for the last 5 years or so, scaling up scalable machine learning, parallel machine learning has been one of the big subfields in machine learning. There was a nice collection of articles in, came out in 2012, Cambridge University Press, or maybe it was MIT Press, I forget which. There's been a long series of workshops on scalable machine learning. In 2013, there was a bunch of popular press stuff. They said big data should be the word of the year, buzz of Silicon Valley. This is actually kind of an interesting story. So in the last presidential election, 2008, one of the big players in that election was a guy named, oh crap, blocking on his name. He's a CMU grad. He was one of the first graduates of the machine learning department. He got a master's in the machine learning department sort of when it first started up. And he was the CTO, the chief technical officer of Obama for America. And one thing they did was they sort of switched from the kind of old models for modeling elections, where you basically had a model sort of at the county level or the census block level to see what that area would do, right? And instead, he built a classifier for basically every registered voter in the United States, several classifiers, whether you're going to vote this way, whether you're going to vote that way, right? Whether you're persuadable or not persuadable, are you actually going to vote or stay home? So that was sort of like in size and complexity of the models. So right now, if you, this was 2014, Google suggests if you type in data SC, you get data science, data scientist. Of course, data science CMU, right? That makes sense. And data science salary, that's an important one. Yeah, salary, skills, sexiest job, shortage. So yeah, data scientist, the sexiest job no one has. Yeah, this is from 2014. So of course, now it's 2016, so all this is over, right? Big data is not the like new kid on the block. The new kid on the block is deep learning, okay, right? So maybe you're in this class because you couldn't get into Roland's class, I don't know. But deep learning is also really very much about big data, okay? So this is a plot from an article that Yoshua Bengio, one of the kind of gods of deep learning, wrote in 2009 when he was arguing at the point you still need to argue that it was effective, okay? So what we're looking at here is sort of two different models, okay? This one is a deep learning model, all right? And he's basically showing it's like, wow, this really does a lot better, okay? But where does it do a lot better, okay? When you have a lot of examples, okay? So this is the number of examples seen, and these are not like integers, so this is not after 8 examples or 9, right? This little thing here is times 10 to the 6, okay? So these are over millions of examples, and the number of examples you really need to sort of even kind of think about doing deep learning in this set of algorithms was actually around here, okay? So this was like 2.5 million examples, okay? That's where it sort of starts off, 2.5 million. And again, you know, looking at the big data, there's a big gap here, okay? So this gap here is basically sort of doing, you know, a naive optimization, just kind of gradient descent, versus a more clever optimization, which was kind of what Bengio was kind of pushing at the time. I think the specifics would change now quite a bit. All right, so this is basically what you can get by being clever, okay? And it's really not that different from what you get going from 1 million to 10 million examples, okay? So scaling up the number of examples by an order of magnitude is part of the story in deep learning as well. That's why we can sort of build complex models. All right. So in this experiment, Yoshua Bengio did like use 2.5 million for what he called examples for pre-training, so an unsupervised step. And again, if you look at what people are doing in deep learning nowadays, right? The first question, if you're going to apply it, is well, where do you get the data? Or what data is available, right? So ImageNet has 20,000 categories, 14 million images, right? That's sort of one of the big success stories of deep learning for vision tasks, right? And what really made it possible with these really big image collections. Another thing in NLP, one thing people are looking a lot is reading comprehension. And again, there's lots and lots of data here. So Bulan did some experiments with these data sets right here. But you know, this is hundreds of thousands of documents, millions of questions. So those are basically the training examples. So we're looking at over 1 million examples. So again, it's a focus on very large data sets. So I'm here at like another break in my technical presentation. Are there questions or comments or disagreements? All right, well, let's go ahead and move on. Okay, so I'm going to spend a little bit of time reviewing something else that's important for this course. You guys have probably seen this before, but I want to talk a little bit about asymptotic complexity. I'll maybe say a couple words about just kind of the focus of the course, okay? So there are some things that I'm not going to emphasize in this course, not because they're not important, but because I feel like they're a little bit too fragile from the point of view of time. So if you're an internship at a company that really cares about big data, you'll probably be working on code in C++, right? You really care about getting things right. This course is not really about how to optimize your code, okay? To the extent I can, it's not really about, the hardware and software that we're going to use today. So we'll be talking, all right, but I'm not really trying to sort of teach you all the details of, say, Spark or Flink, right? What I really want to kind of make sure you leave this course with is, understanding of what the kind of intrinsic costs of the operations you're going to do are. And even though computers have been moving really fast over the last, 50 years, right? Hardware is changing all the time. There's all these differences. There are some sort of kind of stable long-term lessons. So you need to understand the cost of what you want to do. You have to understand what the tools that are available can offer. Okay. For really big data, you can't afford to do something that's cubic or quadratic, right? You have to really look at things that are linear time or nearly linear time, right? So you can take data, you can scan through it, you can sort it. There's not that many other things you can do with linear time operations. But there's a lot of things you can do by composing these operations in a clever way, okay? So that's another thing that you need to understand, okay? So another thing is basically how do you organize your computations, right? So some of the things we'll be talking about will be parallel machine learning. Sometimes they'll be talking about, basically using hardware effectively when you've got a small amount of memory and, lots of data that you need to stream through from disk. So another thing I want to emphasize is understanding how to organize computation so they use what's fast, okay? And there's also, this is something that's very hard to teach, but I want to understand you guys to understand how to test and debug programs with large data sets. So that's another kind of theme, okay? So this is what I think this is about. And one of the things we kind of need to talk about is complexity. So I've already talked about this several times. I talked about linear operations. One of the kind of basic tools here is asymptotic complexity. Okay, so this big O notation means that this function f grows no faster than g in some kind of loose qualitative sense, right? And specifically, the qualitative sense is at some point, when my input n is large enough, okay, then f of x is bounded by g of n up to some constant, all right? So that's what we mean by the big O notation. At some point, this starts looking like, it's upper bounded by some constant times g. And this is sort of the same thing except with a lower bound. So the omega means there's a lower bound, okay? So, there comes useful rules to understand when we're talking about the complexity of algorithms. So if I've got an order n to the fourth step and an n cubed step, all right, for big data, this n cubed doesn't really matter. The n4 is going to grow much, much faster. So you can just kind of throw that away at some point, okay? So only the highest order terms matter. Because we're talking about things up to a constant, the leading constants don't matter. So this is also order n to the 4, okay? Another thing is like if you have a degree, the log of a polynomial, and you can sort of simplify that and put that in front. And then, again, it kind of goes away. So these are some kind of useful simplifications to kind of think about. So just putting this in the context of the rule pruning, let's just do my informal argument a little bit more carefully. Okay. So we have n examples, m conditions in the rule set. So growing the rules takes time omega m times n. All right. And that's based on the assumption that evaluating each condition C is omega of n. All right. So this is a lower bound. So we're using omega instead of O. Okay, so when the k% of the data is noisy, okay, the claim is that you can't really compress that data. Okay, so k%, it means 1/100th times k, right? So n times 0.01 times k, within a constant factor will be the number of rules that you have. Each rule is going to cover a constant number of examples. So then growing the rules is going to be omega of n squared. Okay, so we can put these things together and come up with a lower bound that way. Okay, And again, we can kind of push through the same thing, and sort of this is omega of n cubed. And that sort of explains these results right here, where we see something that's qualitatively n cubed in our log-log plots. So we kind of know how to do this, but let me talk for a couple of minutes about something else which is really important. Okay, so these asymptotics break down either if the data set isn't big enough, okay, or if you have some operations that are much more expensive than other operations. Okay, so when the constants get really big, it's no longer productive to ignore them. Okay, there's another interesting case in machine learning, right, which is when we can't really predict what the program's going to do, right? If I know it's linear time in each iteration, but I don't know how many times I'm going to iterate, it doesn't help me figure out what the time complexity is. So often, analysis of machine learning systems involves some sort of mix of analytics, right, like the stuff I kind of showed you, and this sort of qualitative experimental procedure. Okay, and let's talk a little bit also about operations with different costs. So the main thing here is we have to really understand what it is that we should be counting, right, and what we can be ignoring. Okay, so how many people have heard of Jeff Dean? Okay, that's a pretty good subset. So he's a famous Google guy. He wrote sort of the first MapReduce platform. So at Google and other places, there are a bunch of like Jeff Dean jokes, which are kind of like Chuck Norris jokes, except more geeky, right? So compilers don't warn Jeff Dean; he warns compilers. Yeah, when he has an ergonomic evaluation, it's to protect his keyboard. If you use GCC with a -O4 option, that's optimization level 4. It just emails your code, Jeff Dean, to rewrite it. And this is my favorite. He puts his pants on one leg at a time like everybody else. But if he had enough legs, you'd realize his algorithm is actually log n. So that's Jeff Dean. So that's my introduction to these numbers. So these numbers that Jeff Dean says everyone should know. These are a couple years back, but they haven't changed too much. Let's look at some of these numbers. So these numbers here are things that are sort of accessing the lower and lower level pieces of the CPU. Okay. So the main thing we kind of care about here is memory versus disk, right? We're not going to talk too much about how much faster things can be when you put things in cache. All right, so a main memory reference is about 100 nanoseconds. A nanosecond is a 1/1000th of a second. Okay, here's another one. So reading a megabyte sequentially from memory, you'd think it would be 1,000,000 times faster than that, right? But memories are actually designed so you can sort of scan through them efficiently. So it's actually faster, okay, right? Instead of being 1,000,000 times this number, it's a 250,000 nanoseconds. Okay. So here's another one. A disk seek is 10 million nanoseconds. Okay. So a disk seek is basically when you have to jump from one location in a disk file to another. Okay. And that's what you do to just read one byte in sort of like a truly random location on the disk. All right. So there are other things you can do in sort of about the same amount of time. So you can also read a megabyte, okay, from the network or from disk. I mean, these numbers are really sort of roughly comparable, okay. So you can read a whole megabyte from network or disk, and you can do it about the same time it takes to do one disk seek, right? And maybe 1,000 times. I'm sorry, about 40 times slower than it takes to do the same thing in memory. So the difference between reading sequentially is about 40x. Okay. And the difference between a random access in main memory and a random access on disk is just enormous, many orders of magnitude. I'm going to try and finish this up next time. I'm a little bit behind, maybe like 10 minutes behind, not a big deal. But I'm going to actually kind of point you to this nice site here. Actually, this is a cached version. But if you Google this guy, you'll get his current version as well. So this is showing you these same sorts of latency numbers. Okay, so these are latency numbers for things, in the processor. Okay, these are things like accessing the cache. Okay, and then we're going to take 100 of these. That's this block right here. And we're going to sort of shrink everything down to these blue blocks. All right. So this is the main memory reference. This is kind of really where things start. Okay. And then we're going up here. 100 of these is the little green box. Okay. So one of these green boxes, so 100 main memory references, is reading a megabyte from memory sequentially. Okay, so that's like 100 times slower than one reference, but you're getting a million things. Okay, then let's do another 2 orders of magnitude. Okay, so we're going up, a factor of 100. Okay, now we're looking at a disk seek. Okay, or a sequential read. Okay, so these are Jeff Dean's numbers visualized. Okay, the really cool thing about this visualization is you can also kind of go back in time. So if we want to go back to where this was 2005, you can sort of see how things have changed. And the interesting thing is not really how much they've changed, okay, but how stable they've been over the last 15 years, right? So you really have to go quite a ways back before these things start to change noticeably. But the orders of magnitude really stay the same. References are going to stay in the blue column. Okay. Reading a megabyte from memory is staying in green. Okay. And the disk seeks are staying there another couple orders of magnitude ahead. All right. And it doesn't really look like it's going to get much better over the next few years, according to his projections. All right. So this is actually something that's part of why big data is a big deal for computer scientists. Okay, so there was a stretch of time when computers got faster every year. Okay, they're still getting faster in some sense. Okay, but really the clock speed is really about the same now as it was 10 years ago. Okay, so disk speed, seek speed has gotten better, but it takes about 10 years for it to double. So it's getting better, but really slowly. Okay. So this basically means if we want to build bigger and bigger data sets, use bigger and bigger data sets, we can't just leave it to the hardware guys to improve everything. Instead, we've got to improve the algorithms so that we can exploit multiple CPUs and so on. All right. I'm going to stop now, and I'll pick this up again on Thursday. Thank you all.